Okay, we're going to start talking about our next series of topics, which is on similarity. And just some background information and kind of to summarize what we've done in dilations. You use vectors to describe translations of the plane. That was when we talked about congruence. And so now in this second set of topics, you're going to have figures bound by the coordinate plane, and we're going to start going back to talking about translations in terms of units, either going to the right or up or down instead of just plain old vectors. And the figures on the coordinate plane rotated at a center rotation will be the origin of the graph. And in most cases, you will describe the rotation as having a center center O and a degree D, unless the rotation can be easily identified, such as if it's 90 degrees or 180 degrees. And of course, reflections will be reflections across a line, but when you want to identify that line of reflection as either the X or the Y axis. So you don't necessarily have to copy these down as notes unless there's something that sticks out for you, but just kind of to give us a little bit of background of where we've been and where we're going. And to continue that, it should be noted that congruence together with similarity is the fundamental concept in planar geometry. If that sounds familiar, the root word of that is plane. And we've been talking about points on a plane, so that's why they call this type of geometry planar geometry. The concept defined without coordinates. In fact, most transparently understood when introduced without the extra conceptual baggage of a coordinate system. This is partly because coordinate systems pick out a preferred point, which is the origin, which then centers most of the discussions of rotations, reflections, and translations at or in reference to that point. And you are then further restricted to only the nice rotations, reflections, and translations that are easy to do in the coordinate plane. And allowing us to do that is a huge mistake because it's really, it's opposite to the main point, antithetical, meaning opposite, to the main point that must be made about congruence, that rotations, translations, and reflections are abundant in the plane. That for every point in the plane there is an infinite number of rotations up to 360 degrees. That for every line in the plane there is a reflection, and for every directed line segment there is a translation. So a lot of this we're going to do on a coordinate plane, but just keep in mind, or keep in the back of your mind, that coordinate planes restrict these types of transformations, and that there are definitely infinite ways of translating, reflecting, and rotating. It is the abundance that helps you realize that every congruent transformation, the act of picking up a figure and moving it to another location, can be accomplished through a sequence of translations, rotations, and reflections. And further, that similarity is a congruence transformation in addition to dilation. And that's going to be the big main topic, is the fact that similarity is obviously a dilation, but it's also a congruence. And remember, congruence is a rotation, reflection, or a translation. All right, so let's go ahead and start our topic about similarity. So dilation alone is not enough to state that two figures are similar. And consider the two pairs of figures we have here. Do they look similar? Go ahead and answer that before you continue on. And if you came up with an answer like yes, they look like the same shape, but they are different in size, then that would be an honest observation. So how could you prove that they are similar? What would you need to do? So again, kind of formulate an answer before you continue on, just so you can see whether you're on the right track. Well, we would need to show that they could become the same size by dilating one of the figures. So hopefully these are similar, and we would have to dilate one figure to see if it will map onto the other figure. would we be able to dilate one figure so it was the same size as the other? And the answer would be yes. We could dilate to make them the same size by using an appropriate scale factor. Obviously, dilations require a scale factor, so as long as we can either come up with a scale factor or create our own scale factor, then that would be possible. We could make them the same size, but would a dilation alone map figure S onto S sub 0? So go ahead and give your best guess. No, dilation alone would not map S onto S sub 0. Probably because they're facing in different directions. So what else should we do to map figure S onto S sub 0? And we would have to perform some sort of translation and a rotation to map S onto S sub 0. Okay, so now we're combining what we did in the last module with similarity in this module. So that is precisely why dilation alone is not enough to define similarity. Okay, just not all shapes are facing the same way or are overlapping, so we can't just say dilation is to similarity. Two figures are said to be similar if one can be mapped onto the other using a dilation followed by congruence, and again a congruence being a sequence of basic rigid motions, or flip that around, a congruence followed by a dilation. So let's take a look at example 1. This is in your packet that you received. Based on the definition, how could we show that triangle A double prime B double prime C double prime is similar to triangle ABC? Remember the work that you did in lesson 3 to bring dilated figures back to their original size. And see if you can work that out. To show that triangle A double prime B double prime C double prime is similar, and notice the symbol for similar is just one squiggly, or one half of the squiggly equal sign. That is the symbol for similarity. So to show that both triangles are similar, we need to describe a dilation followed by a congruence. We want to describe a sequence that would map triangle A double prime B double prime C double prime onto triangle ABC. There's no clear way to do this, so let's begin with something simpler. How can we map triangle A prime B prime C prime onto triangle ABC? That is, what is the precise dilation that would make triangle A prime B prime C prime the same size as triangle ABC? Well, a dilation from the center 0 with a scale factor of r equals 2 would accomplish that. Remember that our goal, though, was to describe how to map triangle A double prime B double prime C double prime onto triangle ABC. So not just A prime B prime C prime, but the double prime triangle. So what precise dilation would make triangle A double prime B double prime C double prime the same size as triangle ABC? Well, a dilation from the center 0 with a scale factor of r equals 2 is going to make that triangle, that double prime triangle, the same size as triangle ABC. All right, so let's take a look at this. This is not in your packet, so if you want to print this out and paste it into your journal, or you can sketch it on graph paper. But we have A double prime, or we have the original figure ABC. We have A prime B prime C prime, A double prime B double prime C double prime, and then A triple prime B triple prime C triple prime. So you're going to have to probably sketch this out before we continue so you can refer back to it. Now that we know how to make triangle A double prime, B double prime, C double prime the same size as triangle ABC, what rigid motions should we use to actually map triangle A double prime, B double prime, C double prime onto triangle ABC? Have we done anything like this before? I would hopefully think you would say yes. Well, we did do this. It was number 2 of the problem set from lesson 2. We had 2 figures dilated by the same scale factor in different locations on the plane, and we had to use a vector translating along that vector to map one onto the other. So now that we have an idea of what needs to be done, let's describe the translation in terms of coordinates. How many units and in which direction will we need to translate so that triangle A triple prime, B triple prime, C triple prime maps onto or maps to triangle ABC. So instead of just talking about a vector, since we've got some guides, we need to be more precise and talk about this in coordinates going up and down. So we would need to translate that triangle 20 units to the left and 2 units down. So following along the grid lines. So now let's take everything that we've done and use precise language to describe how to map triangle A triple prime, B triple prime, C triple prime onto the triangle ABC. We will need information about the dilation and the translation. So give it your own shot first before you continue on and see if your precise language matches what is given. So you should have said something like this. The sequence that would map triangle A double prime, B double prime, C double prime onto triangle ABC is as follows. Dilate triangle from center O by scale factor of r equals 2. Then translate the dilated triangle, which is again A triple prime, B triple prime, C triple prime, 20 units to the left and 2 units down. All right, since we're able to map triangle A double prime onto triangle AABC with a dilation followed by a congruence, we can write that triangle A double prime, B double prime, C double prime is similar to triangle ABC. And in notation, it would look like this. Triangle A double prime, B double prime, C double prime is similar to triangle ABC. All right, let's take a look at another example. So when we get to the next slide, again, stop the video and sketch this out in either on graph paper or in your math journal. You're going to have a triangle DEF that has been dilated from the center O by a scale factor of r equals 3. It is going to be noted as D prime, E prime, F prime. And then you also have a triangle D double prime, E double prime, F double prime, which is congruent to triangle DEF. And again, congruent, the symbol for congruent is the equal sign with the squiggle on top of it. So go ahead and pause the video, sketch this out in your graph paper so that you can refer to it as we continue on. All right, so we want to describe a sequence that would map triangle D double prime, E double prime, F double prime onto triangle DEF. This is similar to what we did in the last example. So summarize the work we did yourself, or look back through what you just written and see if you can apply that to D double prime, E double prime, F double prime, how we can map that onto DEF. So it should look something like this. First, we figured out what the scale factor would be to make the triangles the same size. Then we used a translation to map the magnified figure onto the original triangle. So what is the difference between this problem and the last problem? Go ahead and take a look at the two of them and what do you see is different? Well, this time the scale factor is greater than 1, so we will need to shrink D double prime, E double prime, F double prime to the size of triangle DEF. And it also appears as if the translation alone will not map the one triangle onto the other. So paying attention to the labels of the points is very important. So now that since we want to dilate this triangle, the double prime triangle, to the size of the original triangle, DEF, we need to know what the scale factor R is required so that the line segment of OF is going to be equal to the scale factor times OF double prime. Okay, no, so not single prime, but double prime. So what scale factor do you think we should use and why? So take a look at it and see if you can figure that out. Well, we need a scale factor of R equals 1/3 because we want the original OF, and that is going to be 1/3 of OF double prime. So what precise dilation would make triangle D double prime, E double prime, F double prime the same size as triangle DEF? Well, that would be, again, dilated from a center of O with a scale factor of R equals 1/3 would make the double prime triangle the same size as the original triangle DEF. All right, so now we should use what we know about rigid motions to map the dilated version of the triangle D double prime, E double prime, F double prime onto DEF. What should we do first? Okay, so take a look at that. So how am I going to get D double prime to be DEF? Well, first we need to translate the triangle D triple prime, E triple prime, F triple prime, which, if you notice, was our shrinking of D double prime. So this was the D double prime, E double prime. We shrunk it down, and now we have triple prime, and now we're going to move it 2 units to the right so that what points are equal, or what point is equal. Well, what should we do next to the translated triangle, the red triangle? So we just took this and moved it over. How can I get this to map onto this triangle, the original one? Well, you're going to need to reflect it across the x-axis to map the red triangle onto triangle DEF. So now that we've done that, use precise language to describe how to map triangle D double prime, E double prime, F double prime onto triangle DEF. Again, look at the first example before you attempt this and see if you can summarize it before moving on. All right, so this is what it should sound like. The sequence that would map triangle D double prime, E double prime, F double prime onto triangle DEF is as follows. Dilate triangle D double prime, E double prime, F double prime from center O by a scale factor of 1/3. Then translate the dilated image of the triangle, and which we call D triple prime, E triple prime, F triple prime, 2 units to the right, and then finally the last thing we did was reflect across the x-axis to map the red triangle or the triple prime triangle onto triangle DEF. All right, so since we're able to map that triangle onto the original with a dilation followed by congruence, we can write that triangle D double prime, E double prime, F double prime is similar to triangle DEF, and in notation it would be triangle sign, and then the double prime symbols, and then our similarity symbols, and so on. All right, here is example 3. In the diagram below, we have triangle ABC is similar to triangle A prime, B prime, C prime. Describe the sequence of dilation followed by congruence. So again, it's telling you the order that it wants you to do this in. A dilation followed by congruence. That will prove that these figures to be similar. So again, sketch this out before going on. So let's begin with the scale factor. We know that the scale factor times the length of AB is going to be equal to the length of A prime, B prime. So what scale factor R will make ABC, or triangle ABC, the same size as A prime, B prime, C prime? Well, you would notice that it is 2 equals 1, so therefore the scale factor is 1/2. That will make ABC the same size as A prime, B prime, C prime. So if we apply that dilation from the origin of the scale factor, r equals 1/2, then the triangles will be the same size. Note that that new triangle is A double prime, B double prime, C double prime. So what sequence of rigid motions would map this dilated image of ABC onto A prime, B prime, C prime? Well, here we go. We could translate the dilated image of the original and of A double prime, B double prime, C double prime 3 units to the right and 4 units down, and then reflect the triangle across line A prime, B prime. So in essence, taking this triangle, move it 3 units to the right, 4 units down so that it is the mirror opposite, and then we're going to reflect it over this line A prime, B prime. So the sequence that would map this to prove the figures are similar is this description. So a dilation from the origin by a scale factor of 1/2, followed by a translation of the dilated version of ABC 3 units to the right, 4 units down, followed by a reflection across line A prime, B prime. All right, example 4. And again, go ahead and sketch this out. This might be kind of hard to read, so I retyped what the line lengths were. So we're going to use ABC is similar to DEF. So notice now that the lettering has changed. We're not using A prime, B prime, C prime. We're actually comparing 2 triangles with different lettering. Notice that ABC means that point A should be the same or corresponds to point D. Point B, it corresponds to E, and C to F. We want to describe the sequence of dilation followed by a congruence that would prove that these are similar. So first we need to describe the dilation that would make this the same size. What information do we have? So look at that again and find some concrete information that helps us describe the dilation. Well, we know the side length of AC and we know the side length of DF, so we can use that to determine the scale factor. Can we use any 2 sides though? Remember, is there something that has to do with corresponding sides? So assume, for instance, that we know the side AC is 18 units in length and EF is 2 units in length. Could we find the scale factor using those 2 sides, AC and EF? Why or why not? So make your best guess, or if you know for sure, go ahead and jot it down. So the answer to that is no. Okay, we need information about corresponding sides. So if we are given one side, we have to be given the measurement of the corresponding side on the other figure. So since AC and DF are the longest sides of each triangle, they are also opposite the obtuse angle in the triangle. Side AC does not correspond with side EF. And if we knew the length of BC, then we could use BC and EF, but we cannot use AC and EF. Those don't correspond. So we can't set that up as a scale factor. So now that we know that we can find the scale factor, if we have information about corresponding sides, how can we calculate the scale factor if we are mapping triangle ABC onto triangle DEF? Well, line length DF is equal to a scale factor times AC, which means 6 is equal to R times 18, and therefore R is 1/3. So our scale factor is 1/3. If we are mapping DEF onto ABC, what would the scale factor be then? That means it would be 3. So it depends on which one you are mapping onto which. So since we're not talking about A prime, B prime, C prime, you need to know the order, which is considered the original, which is considered the other shape or the dilated shape, or when you're describing it, you need to pick which one you're mapping onto which. So depending on the order that you're doing, you could either have a scale factor of 1/3, or you could have the reciprocal, remember that? The reciprocal of 1/3, which is 3. So depending on which way you want to go with this. So what is the precise dilation that would map ABC onto DEF? So now we're given the direction we are going. We're doing ABC onto DEF. All right, that would be 1/3. Okay, instead of 3. So to map this onto DEF, we have to shrink it down. So we have A prime, B prime, C prime, and we've shrunk it by 1/3. So now we have to describe the congruence. So now we have this shape that hopefully is the same as this shape. Okay, now we need to get this over here so it maps on top of it. So determine the sequence of rigid motions that would do that. Well, you could dilate the version of ABC 7 units to the right and 2 units down. Then you're going to have to rotate it d degrees around point E, okay, because our points are matching up. So that segment B prime C prime maps onto segment EF. This should sound familiar from our last unit. Finally, reflect across the line EF. So if that doesn't make sense, write it out or check it in your drawing and see that that doesn't work. So note that d degrees refers to a rotation by an appropriate number of degrees to exhibit similarity. You could choose to describe this in other ways, or you can even go in a slightly different order. But since we don't have a protractor to measure exactly how many degrees, we're going to use d degrees. There is some number of degrees to get that line segment B prime C prime to map exactly onto segment EF. All right, so the sequence of a dilation followed by congruence that proves that triangle ABC is similar to DEF is as follows, and you can read that. It's just a summary of what we just did. All right, example 5. So again, sketch this out on your graph paper, knowing that a sequence of dilation followed by congruence defines similarity also helps determine if two figures are in fact similar. So the question is triangle ABC able to be mapped onto DEF? So do we have a similarity here? All right, the question is no, or the answer to that would be no, because by the fundamental theorem of similarity, we expect corresponding sides lengths to be in proportion and equal to the scale factor. If we compare sides AC to DF and BC to EF, because again, corresponding sides, we would get 18 to 6, but then we would have 15 to 4, and they are not equivalent fractions or equivalent ratios by any means. So we don't even need to do any congruence testing because we already know that these two are not dilations of each other. So therefore the triangles are not similar because the dilation will not map one onto the other. All right, last example. Again, knowing that dilation followed by congruence, and notice that congruence is kind of highlighted there. A dilation followed by a congruence defines similarity, also helps determine if two figures are in fact similar. For example, would a dilation map figure A onto figure A prime? Is figure A similar to A prime? Now you might be looking at this going, really? You're asking me this question? But if you look at it a little bit closer, do we have two sides that are corresponding? And the answer to that is yes. This side right here, 16 units, corresponds with this side, 8 units. And this side, 24, corresponds with this side, 12. So in actuality, we do have sides that correspond with each other. However, we have corresponding sides that are proportional, but there is no single rigid motion or sequence of rigid motions that would map a 4-sided figure onto a 3-sided figure. So proportionally, those two sides are similar. However, now we're talking about the type of figures, and obviously a 4-sided figure is not going to map onto a 3-sided figure. Therefore, the congruence part is not fulfilled. So the dilation worked out, but the congruence will not work out, and therefore figure A is not going to be similar to figure A prime. All right, so here's where you go back to your exercise sheet, complete exercise 1 through 4 on the sheet, and then go ahead and continue on with this video so you can check your answers. All right, here is the results for problem 1. And I'm just going to keep going through these. You can stop the video if you need to read them. And problem 2. And problem 3. And the last one, problem 4. All right, so to summarize, we know that a similarity is defined as a sequence of a dilation followed by a congruence. So that is why we have moved off of dilation, and now the definition of similarity is it's got to be a dilation, but then you need to check for congruency. And last but not least, to show that a figure in a plane is similar to another figure of a different size, we must describe the sequence of a dilation followed by a congruence, one or more rigid motions that maps one figure onto the other. Notice that we always start with dilation first, and then we follow it by a congruence. All right.